Hi everyone, we gladly welcome you to the 2023 Expressive Development Conference. I am Jian Gang, the Director of Application Engineering at Expressive. The topic of today's session is Expressive HMI Smart Display Solution. In the following presentation, my colleague and I will introduce practical chip selection guides and development experience for Expressive Smart Display Solution. This presentation is divided into four main sections. First one, brief overview of market trend. Second, expressive LCD solutions and chip recommendations. Third, application development guide based on ESP idea. Fourth, anti-tearing strategies for LCD displays. Yeah, we are from Expressive Application Engineering team. Our team plays a vital role in providing comprehensive technical support and assistance to customers and their partners using expressive products and solutions. We are committed to providing innovative and reliable wireless intelligent solutions for a connected world. Now that we have a clear understanding of the agenda we will cover today, let's move on to the first section, where I will provide a concise overview of the market trends in the field of display application. Additionally, I will share the opportunities and advantages of expressive Wi-Fi MCU in this evolving landscape. In the current era of 5G and AIoT, the application of LCD screens has expanded beyond traditional areas, such as smartphones, tablets, and automotive displays. In smartphone scenarios, appliances like refrigerators, washing machines, air conditioners, microwaves, induction cookers, and robotic vacuum cleaners are increasingly incorporating LCD screens. The interaction in screen applications has also witnessed diverse developments. First, from resistive touchscreens to capacitive touchscreen, from single touch to multi-touch capabilities. Touchscreen has become an indispensable part of modern embedded systems, with an increasing number of LCD screens integrating touch functionality, enhancing the user experience through direct finger input. Secondly, as voice recognition technology rapidly advances, there is a growing demand for voice interaction in modern smartphone products. Users can remotely control devices through voice commands, simplifying the operation process. In addition to online voice recognition, the need for seamless wake-up and offline voice recognition is also increasing. Moreover, in daily life, many simple yet precise interactive operations, such as adjusting the brightness and color temperature of light or opening and closing curtains, can be achieved more quickly, accurately, and conveniently by combining LCD frames with knobs. We can already see that in appliances such as microwaves, washing machines, and water heaters. This development in LCD screen applications and interaction methods showcase the continuous evolution and increasing versatility in the HMI environment. Now, what are the advantages of LCD products driven by Wi-Fi in the future? Firstly, the key advantage is its high integration. With a single Wi-Fi MCU chip, the LCD product can deliver UI display, screen control, voice interaction, Wi-Fi, and BLE functionalities. This not only reduces hardware costs, power consumption, and size, but also simplifies software development and maintenance. Secondly, the lightweight operating system is a major benefit. By utilizing a lightweight real-time embedded OS like FreeRTOS, the system requires fewer hardware resources, lower power consumption, and provides faster response speed. It's a perfect fit for efficient IoT product development. Lastly, LCD solutions offer versatility. They can integrate smart home control, health monitoring, entertainment, and security features. Users can customize smart control scenarios based on their specific needs, enhancing the visual appeal of smart central control products while providing a delightful user experience. Now that we have gained insight into the market trends and the evolving landscape of LCD applications, let's move on to exploring expressive LCD solution and the recommended chips that empower these smart displays. To begin, let's take a comprehensive look at how expressive chip series support specific LCD screen interfaces. The ES32S series and ESP32P series chips now offer support for interfaces with higher transmission bandwidth, such as RGB and BPDSI. These chips can drive higher resolution screens. To facilitate chip selection, we have considered the performance, power consumption, and cost requirements in both IoT and LCD application scenarios. Currently, our focus is on three main chips: ESP32C3, ESP32C6, and ESP32S3. We have categorized them based on several common LCD resolutions, and you can find more details in the provided table. Now, let's move on to the solutions. First, I will introduce the knob screen solution. Knob screens are known for their simplicity and user-friendly interface. Instead of searching for and tabbing specific buttons on the screen, users can control devices by simply rotating the knob. This provides better user experience, especially in scenarios like controlling lights in a dark environment. Expressive offers a complete knob screen solution for 1.28-inch SPI and 1.6-inch QSPI interface round screen. It includes logic for UI interaction and design guidance for product structures. Novel interaction has become a cost-effective upgrade solution for widely recognized and adopted by home appliance manufacturers. With its small chip package, expressive solution seamlessly integrates with various well-designed node structures. Next, let's talk about the central control panel market. Central control screens serve as a core control center for smart home systems, enabling control and monitoring of various smart devices within the home, such as lighting, temperature, security, music, and appliances. Users can conveniently control all the devices in their smart home system from one central control screen, providing a seamless and efficient experience. For 3.95-inch 480 plus 480 resolution and 4.3-inch 800 plus 480 resolution RGB interface screen. Espressif offers a smart central control solution based on the ESP32S3 chip. This single-chip solution integrates wireless connectivity, your display, offline voice recognition, and screen control functionalities. Additionally, the central control screen can serve as a gateway for smart homes, utilizing the powerful Wi-Fi mesh and VoE networking capabilities to centralize the control of various devices within the home. If you are interested in the development boards and solutions discussed in this presentation, we encourage you to get in touch with us through our business contacts. Lastly, let's discuss the Visio doorbell market. This doorbell utilizes cameras to provide users with real-time video of visitors on the screen. They also feature a microphone and a speaker for two-way communication with visitors, as well as remote monitoring capabilities through cloud connectivity. Video doorbells have become popular smart home devices in the market. Espressif recommends a video doorbell solution based on the ESP32S3 chip. This solution incorporates a 720p USB camera and an RGB interface display screen with an 800 plus 480 resolution. It supports local video decoding and screen refresh rates of up to 15 fps. The ESP32S3 chip natively supports USB 2.0 and offers a rate that will prefer resources, eliminating the need for additional USB chips or DSP chips. With this single chip solution, you can achieve front-end audio processing, voice interaction, HMI interaction, and real-time network calls, all at a highly cost-effective value. Next, we will move on to the most crucial and informative section of this presentation. In this section, my colleague will give you a through of software development process for LCD solutions and share our experience in dealing with the tearing effect. Yeah, welcome Liu Zhongwei.
Hi everyone, I'm Apple software engineer from Expressive Application Engineering team. In the following chapter, I will dive into the development guide and cover top topics such as framework, driver porting, and application development. First, let's take a look at the hardware frameworks of the LCD solution. These frameworks help us understand how LCDs are driven. For most ISPI and IAP LCDs, ESP can use the same interface to transmit commands and the area size color date to the LCD IC. And the LCD IC stores these states in its internal frame size graphics drive, which is usually called GRAM. Then it displays the color dates from the DRAM on the panel at a fixed refresh rate. It's important to note that these two processes are asynchronous. For most RGB LCDs, ESP uses a three-way SPI interface to transmit commands and uses an RGB interface to send frame size color dates. Since the LCD IC lacks an internal drive, it directly displaces the frame size color dates onto the panel. These two processes are synchronous. When comparing these two hardware frameworks, we can see that RGB LCDs, unlike other LCDs, require ESP to use two different interfaces for transmitting commands and color dates. It also demands ESP to provide a frame-size DRAM. Since the space of DRAM is limited, we often place the DRAM in piece drive. In addition to that, for QSPI LCD, different ICs may require different driving methods. For example, SPD2010 has a DRAM, and its driving method is similar to the live framework. However, SD77903 doesn't have a DRAM, and its driving method is similar to the RIDE framework. However, both of them use a single interface for transmitting commands and data color. Since the QSPI driver is not universal, I want to introduce it further. For screens with a touch IC, ESP can read the coordinates of touch points through either iCloud or SPI. Now, let's explore the software framework, which is primarily composed of three layers: the SDK layer, the driver layer, and the app layer. Firstly, in the SDK layer, we use ESP IDF as the foundational part. It not only includes the necessary peripheral drivers for LCD solutions, such as I2C, SPI, IAT, and RGB, but also provides users with the unified APIs through the ESP LCD components to interact with the screen, enabling operations like refreshing, inverting, and mirroring. Lights is the driver layer. We need to port the drivers for the display device and the input device, such as different modules of LCD IC and Touch IC. Additionally, we use these device drivers to implement the porting of LVGL. Lastly, in app layer, we can directly develop GUI applications based on LVGL. Based on proceeding framework, we have summarized the following five development steps. Firstly, initialize the required peripherals, then create a display device and the input device, like port LVGL. Finally, design the UI. I will explain them using existing code examples. For devices with I2C, SPI, or IAT interfaces, the first step is to initialize the related path. Then we can use the ESP LCD component to install the panel IO instance. Taking the SPI device as an example, the code is shown in the figures. For devices with an RGB interface, most of them use a three-way SPI interface for transmitting commands, where the RGB interface is used to transmitting color data. Since ESP's SPI hardware doesn't support long-byte aligned state transmission, we have developed the ESP LCD panel IO addition component, which debunking the three-way SPI interface. We can use this component to create the panel IO instance. This step can be skipped for LCDs that don't require initialization. Based on the panel IO instance, we can use these APIs to implement functions like transmitting color, dates, or commands. Next step is to create a display device. Currently, ESP-IDF and the component registry support various LCD drivers. For example, we can create uh, we can create an ISP7789 device based on the Pino IO instance. The code snippet for this is shown in the figure. It's important to note that vendor-specific initialization can be different between manufacturers. We should consult the LCD supplier for initialization sequence code and make necessary modifications to the driver as shown in the figure. If the required device is not supported, you can refer to existing similar drivers for porting. We can also create the required input device based on the Pino IO instance. The component registry also supports various touch drivers such as GT911, FT5X06. What's more, it also supports node and the button drivers, which is also served as input devices. The next step is to port LVGL. The detailed introduction of this part can be seen in the LVGL official documents, and other LCD examples in IDF have implemented LGL porting. For SPI and IAP LCDs, we can also use the ESP LVGL port component. However, this component currently doesn't support RGB LCD, but we can refer to the ESP32S3 LCD UA port ESP for implementation guidance. Finally, we can design UI by coding. Here is a simple demo. Create a button, set its position and size, then register a callback function for events. Of course, LVGL provides us a lot of examples. However, we can also use the Squarelight Studio software, which is a visual UI editor alongside LVGL, allowing users to design beautiful UI through a graphical interface and directly generate code. Currently, it supports various ESP development tools, including ESP Box, ESP Star, ESP32S3 LCD board. Regarding the introduction to the LCD development guide mentioned above, due to time constraints, I welcome everyone to reach out and discuss more interesting topics with us. In the upcoming section, I will delve into the topic of screen tearing. Screen tearing is a commonly encountered issue in LCD applications, which can negatively impact the viewing experience and the overall visual quality of the display. I will discuss its causes and share our experience in dealing with this problem. First, what is screen tearing? Is also known as tearing effect and often appears when there are GUI pins, resulting in a frame that includes two different parts, causing a noticeable discontinuity on the screen. These two pictures were taken while running LVGL demo, and you can see the screen tearing is evident. So, how does tearing appear? I will demonstrate it later with an animation showing the process of screen refreshing. But first, let's take a look at this static diagram. It consists of two parts, GRAM and Pino. GRAM represents the storage area, where ESP can directly read color data, and panel represents the visual area, where the LCD reads from DRAM and display on the screen. As you can see, screen refreshing primarily involves the process of DRAM's writing and reading. Here, let's assume that the speed ratio reading between writing and reading is 1 colon 3. Start the animation. We can see that when the read position overlaps the write position in the middle area, the second frame on the panel appears tearing, which lasts for 1 frame duration and is noticeable to the human eye. Let's see again. Uh, Now let's try to increase the write speed to achieve a ratio of 1 colon 2. Start the animation. We can see that the read position aligns with the write position at the end of a frame. No tearing appears. Therefore, when the write speed is less than half of read speed, tearing will appear. In fact, tearing can also appear when the write speed is more than twice the read speed, but this situation is unlikely to happen. Additionally, in previous demonstration, we assumed that the initial states of writing and reading were synchronous. Obviously, when this condition is not met, even if the write speed meets the requirement, tearing is likely to appear, as shown in the animation. We can summarize the causes of screen tearing as follows. The first one is single DRAM, and another one is improper coordination of reading and writing. If the write speed is less than half of read speed, or if their initial states are not synchronous, it can cause screen tearing. Here, we adopt different strategies for different types of LCDs. For SPI or IET LCDs, we use T signal, while for the RGB LCDs, we use multiple DRAMs. First, let me explain the strategy of using the T signal. Since LCD ICs with SPI or IAT interfaces have a single built-in DRAM, and its write-read operation cannot be controlled by the ESP. So we can only prevent tearing by controlling the write operation. And it also required for LCD to provide the T signal internally. The timing diagram showing the figure represents the T signal output by a specific LCD IC. It indicates the end of a frame and the beginning of next frame. So we can use the T signal to synchronize the read and the write operations. As shown in the animation, we start the read-write operation when the T signal is detected. Of course, we also need to ensure that the write speed is equal or greater than half of the read speed. This way, we can avoid screen tearing. Since LCD ICs with RGB interface don't have a built-in GRAM and rely on the ESP to provide it, its read operation can be controlled by the ESP. Therefore, we can prevent tearing by using multiple DRAMs and synchronizing the write and the read operations. Let's take a look at this animation. The write and the read operations are performed on two separate DRAMs. Before starting to write to DRAM 1, it has to wait for the reading of DRAM 1 to finish. Then we can swipe the DRAMs and begin a new cycle of read and write operations. Actually, by adding one more DRAM, we can get rid of waiting time for reading because there will always be a DRAM available for writing. The trick here is how we handle this DRAM. For all the details, you can check out the implementation in the ESP32S3 LCD code ESP. That's all. Thank you for watching.